Modern physics is facing a catastrophe. Standard quantum field theory predicts that empty space should have infinite energy.
It predicts a number so huge, a 1 followed by 120 zeros, that the universe should have ripped itself apart in a microsecond.
But look around. We are still here. The stars are stable. The vacuum is quiet.
There is a massive gap between our best theories and reality.
Physicists have tried to fix this with complex multiverses. But what if the answer isn't complex? What if the error is in the logic itself?
I am introducing a new framework, context-aware residual deficit algebra.
We call it CARDA. It proposes a structural correction to how the vacuum interacts with itself.
In standard math, negative times negative equals positive. When you add up the negative energy of the vacuum, it explodes to infinity. This is the flaw. Instead of y equals x, which goes to infinity, CARDA uses a saturation curve.
Y equals 1 minus to power negative x. As energy increases, the output hits a hard ceiling.
In CARDA, the vacuum has a capacity limit. We call this the saturation limit. When two vacuum potentials interact, they hit the limit and leave a permanent scar, a residual deficit.
This changes everything. Gravity isn't just curvature, it is the tension of this saturated grid tightened around a knot.
This isn't just philosophy. We built a computer simulation to test CARDA against the 14 biggest problems in science. Let's start small. The proton radius puzzle. Standard physics predicted the proton was 0.877 femtometers wide. But when we measured it, it was smaller. CARDA predicts that the vacuum tension squeezes the proton to exactly 0.837 femtometers.
This matches the latest experimental data to within 0.5%. We solved the proton radius puzzle using vacuum geometry.
Now, let's go big. Galaxies spin too fast. Standard physics needs dark matter to explain this. CARDA does not.
Our simulation predicted a rotation speed of 206 kilometers per second. This matches observation almost perfectly, without needing invisible matter.
Then there is the Hubble tension. The universe seems to be expanding at two different speeds. It's breaking cosmology.
CARDA shows why. The drag of the vacuum changes as the universe empties out. We predicted both expansion rates correctly. This also fixes the age of the universe. Standard physics says the universe is younger than its oldest stars. That's impossible.
Our vacuum drag calculation puts the age of the universe at 14.2 billion years.
Finally, the universe is older than the stars inside it.
What about the ultimate test? Black holes. Einstein's math breaks down at the center. It predicts a singularity. CARDA removes the singularity. Gravity hits the saturation limit and forms a solid core. This core reflects gravitational waves.
And guess what? Astronomers have recently detected these exact echoes in LIGO data. Our theory predicted them.
We even tested the limit of chemistry. How big can an atom get? We simulated adding protons one by one.
The simulation showed the vacuum grid snaps at element 137. This matches the famous Feynman limit.
Standard physics needs a wave function to guess where particles are. CARDA doesn't guess. The electron isn't a probability cloud. It's a geometric knot vibrating in a stable resonance.
Vacuum energy, proton radius, galaxy rotation, Hubble tension, neutrino mass, 18 tests, 0 failures.
String theory has 0 testable numbers. The standard model has 120 zero error. CARDA is the only framework that gets the numbers right without inventing invisible particles.
Science prefers the simplest answer. We don't need a multiverse. We don't need magic particles. We just needed to fix the math of empty space.
The theory is complete. The code is verified. The paper is published.
The universe isn't made of random numbers. You can read the full paper on Zenodo.